I will go ahead and introduce our speaker, Amanda Chappel. So Amanda is a PhD candidate at the University of Florida in the Engineering School of Sustainable Infrastructure and Environment, in association with the Center for Coastal Solution, or CCS for short. Since starting with UF in 2021, Amanda's research has focused on coastal ecosystem dynamics and how these processes are altered by human activity and global phenomena to support adaptive management strategies. Amanda received her bachelor's and master's at the University of South Florida in environmental science with the geosciences department. While at USF, Amanda was a scientific technician with the Florida Fish and Wildlife Conservation Commission in the Coastal Wetlands Program, where her research was focused on quantifying carbon storage and chronic stressors such as hurricanes and hydraulic alterations on coastal wetlands. When not doing research, you will find Amanda fishing, the Nature Coast marshes, or in her garden if the tides aren't good. And so with that, please join me in welcoming Amanda.
Hey everybody, can you hear me all right?
Yes.
Lovely. All right, so thank you so much for hosting me today. I have really been looking forward to sharing some of my research, which I've been doing for my PhD. And since this is Nature Coast Currents talk, I thought it would be fitting to have a Nature Coast sunset photo on my title slide that I captured this Memorial Day, one of my favorite areas to fish and recreate in general. So first, I want to give my acknowledgments to my many co-authors who have contributed to this research in a plethora of ways, including guiding me along the way and also reeling me back in when it comes. I go to them with another project idea, although I have plenty of data for my dissertation, so I thank them for that. And to the many field and lab hands that have been involved in this research and have really been essential to keeping my head above water, and to the institutions that have provided funding, identity, and community support that have made this research possible. And lastly, to UF, IFAS, and Florida Sea Grant for providing this opportunity to share this research with you all. So where we're going today, first I want to give a brief intro into some estuarine concepts that have guided the development of this research, and then I will be discussing the study area and the Piney Point wastewater discharge event that acts as a case study for these efforts. Then I'll go into two aspects of the project, recreating the sedimentary record near the discharge locations to assess the potential for legacy nutrient storage, and how this event impacted seagrass habitats. And then lastly, wrap up with some takeaways and next steps. So first, I want to introduce you to some broader concepts, the first being the aquatic continuum. And this is simply that Earth systems are all intimately interconnected across landscape, water, and the atmosphere. Some address this as a freshwater marine continuum, as our inland waters are a major driver of coastal water quality, and those are further driven by landscape or watershed inputs as well as atmospheric contributions. So our coastal waters are that ultimate recipient for watershed activity where infrastructure design and longevity can have implications on surrounding systems. And this schematic is specific to carbon. However, this is also applicable to nutrients and pollutants from the watershed and atmosphere into aquatic systems. The second concept is cultural eutrophication, which is where human activities, including industrial, agriculture, and urban, contribute high nutrient wastewater to aquatic systems, which can lead to imbalanced biogeochemical cycling, causing ecosystem disequilibrium. An example of this, which many of you are likely familiar with, is the eutrophication that has been occurring in the Indian River Lagoon on the east coast of Florida for many decades, which contributed to an extensive algal bloom event that occurred in 2016 that caused massive fishery and marine life die-off and extensive loss of seagrass habitat, which is what the schematic here depicts. And when extensive bioavailable nutrients like nitrogen and phosphorus are loaded into these downstream recipients, like coastal waters, some get exported to the open ocean, and then some make their way into the sediments, and then some stay within the water column and can trigger an uptick in certain phytoplankton or algal species within the water column, leading to bloom events. And phytoplankton have short life cycles, so the nutrients they assimilate into their biomass while in the water column eventually gets deposited into the sediments with organic matter. And this organic matter then begins to decompose, leading to an increase in oxygen demand by the microbes breaking it down, which then in turn can create low oxygen events such as hypoxia, where there is limited oxygen available for other aquatic life like fish and marine mammals. And if nutrients continue to be loaded to the system, including from decomposing fish, then positive feedback cycles can develop that can have long-term implications known as a legacy effect on estuaries when conditions allow, where nutrients stored in the sediments can be regenerated and resuspended into the water column during storm events. And when thinking about this concept, it's important to keep in mind that many parameters affect the long-term implications of eutrophication in a system, including but not limited to quantity and frequency of the nutrients being loaded, the bioavailability of said nutrients, water residence time, sediment type, conditions of the buffering habitats like the coastal wetlands, oyster reefs, and seagrass in the area, and frequency and severity of storms that make landfall in the area. Now, getting into the estuary of interest, the Tampa Bay estuary is located on the west coast of Florida and is recognized as the largest open water estuary in the state. Tampa Bay is a really good example of a system that faces both chronic and acute stressors with an extensively urbanized watershed that is approximately 2,200 square miles and supports a population of more than 3 million people. And this system is generally known as a shallow well-mixed system. However, water residence time, how long a water particle stays in a system before getting flushed into the Gulf, varies between the upper reaches and the mouth of the bay, which is an important factor to consider when you're assessing the impact of nutrient loading, as mentioned before. And despite all of the anthropogenic activity surrounding the bay, the system is known as a management success story that has been on a recovery trajectory since the 1980s, following improved nutrient regulations, with a focus on nutrient loading and long-term monitoring effects. And these management changes led to seagrass coverage increasing since the 80s, with coverage peaking in 2016. And this was followed by a decline in coverage between 2020 and 2023, which we will get more into in the second half of this talk, but suggests that ecosystem health has shifted in recent years. So relative to our study area, we collected data from sites outside and inside Tampa Bay for both seagrass and water quality. We had 2 seagrass control sites and 1 water quality control site outside of the bay in a relatively pristine estuary called St. Joseph Sound. And we had 3 sites within the bay, 1 in middle and 2 in lower Tampa Bay for both seagrass, those green circles, and water quality sites, those blue squares. And then there are 2 sediment coring locations that we established near wastewater discharge locations represented by the orange triangles, which we identified as back bay depositional areas. And these sites were established within the projected path of a wastewater discharge event that occurred in April of 2021 from a fertilizer waste facility called Piney Point, where over 800 million liters of high nutrient wastewater was discharged into the bay in just 10 days. So this study was leveraged to better understand the effects of an acute eutrophication event on water column processes, sedimentation dynamics, and seagrass habitat. And since this facility was not only a storage facility for phosphogypsum, which is the byproduct of phosphate fertilizer production, but was also a processing facility for diammonium phosphate for over 40 years, the discharge wastewater was also very high in ammonium. So that 10-day discharge exceeded the annual external nitrogen loads to Tampa Bay, loading over 800 metric tons into the lower portion of the bay. And the 2021 discharge event was not the first occurrence of discharges into the bay. The facility suffered engineering challenges for over 50 years. So this timeline represents the numerous large-scale historic release events that have taken place since the early 1970s into the Tampa Bay estuary. And many of these release events were documented to impact water quality and ecological services within Tampa Bay, which resulted in harmful algal bloom, fish kills, and even seagrass loss. And the most notable and well-documented events were those that occurred between 2001 to 2004, 2011, and that 2021 event. So the cores collected in Piney Point Creek, located north of the facility, was the receiver of part of the 2021 discharge event. And the core located in Bishop Harbor, which is more of an open embayment setting south of the facility, was the receiver of the 2001 to 2004 and 2011 discharges. So, since this facility has such a rich history of discharging wastewater to the bay, our interests were piqued to reconstruct the sediment record to see what insight may provide relative to historic discharge events and whether these legacy nutrients and radioisotopes stored in the sediments, since sediments are known to be that ultimate sink of pollutants. And we can use the sediment record to study historic events in most systems due to the law of superposition, which is a major principle of strata, where within a sequence of rocks or sediments in this case, the oldest layers are at the base, with younger layers progressively found in ascending order atop those older layers. So here I have an image of the sediment core that was retrieved from Piney Point Creek with the approximate depth associated with the 2021 and 2001 discharge events. At the middle, at the top, associated with 21, and the middle of the core associated with 2001. So down core sampling included core into physical refusal at approximately 50 centimeters using the sediment water piston core that's pictured here. And we then took these cores back to the lab and we sectioned them in 1 centimeter intervals from top to base to preserve that different strata. We conducted many analyses on the samples. However, I will discuss a few of them today, but feel free to reach out if you have more interest. So we measure the radioisotopes in each interval as a way of dating the sediments relative to when it was deposited in the system. So radium-226 and lead-210 radioisotopes are very insightful because phosphogypsum is known to be high in radioactive elements, in particular radium-226. And lead-210 has a half-life that's well suited for the time scale of interest, which simply means that this radioisotope decays at a known rate, which can be applied to the quantity of lead-210 measured at different points in the core to give us the age of the sediment layers. We then use the age to determine accumulation rates of sediments and nutrients and assess the quantity of radioactive isotopes in the sediment layers to determine if peak quantities correlate with historic release events from the Piney Point facility. We also performed analytical analyses to determine the concentration of different nutrients and elements to better understand the composition of the sediment and to determine if elements specific to the phosphogypsum facility had been preserved in this record. So getting into the data and what interpretations can be made from our results, here I have graphed the activity of radioisotopes in decays per minute on the x-axis against depth in centimeters on the y. The radium-226 activity, those green lines, which is a radioisotope again found in high concentrations in phosphogypsum, was highest during discharge timeframes in both cores, supporting the study areas likely recording those historic discharge events. Excess lead-210 activity, those red lines, also suggested that the episodic wastewater discharge events were recorded in the sediments, represented by variable decay curves in the top 25 centimeters of the core, where bulk homogenized material was deposited during those phosphogypsum discharge events from the Piney Point facility. And beryllium-7 and thorium-234 activities were also measured in these cores, which were used to confirm that bioturbation was constrained to the top 3 to 5 centimeters of both cores. And the radioisotopic activities at Bishop Harbor were higher than those measured in other Florida estuaries, which tells us that an industrial signature from this facility is plausible. And so all this really means is that it was appropriate to use the radioisotopic activity in our age depth model to determine our sediment and nutrient accumulation rates. And age depth models are often strengthened by independent radioisotopes like cesium-137. However, since cesium wasn't detected in these cores, we used other chemical markers that were abundant in phosphogypsum to do so. Of particular interest to this study was calcium, sulfur, iron, aluminum, and magnesium, which are elements that are known to be high in concentrations in phosphogypsum stacks, including at Piney Point. So our calcium and sulfur, which you can see here in the down core profiles as our teal triangles and dark blue squares, exhibited elevated concentrations during discharge timeframes, corroborating the inference made from the radioisotopic activity seen in that last slide, with calcium displaying the highest concentrations and the clearest peaks corresponding to the discharge event, followed by sulfur. So again, this data simply allows us to have confidence in the age depth model that we used to get our sediment and nutrient accumulation rates, which was beneficial since our lead-210 activity didn't follow a typical exponential decay, likely due to the inputs of radioisotopes from the Piney Point facility historically. So now that I have probably given you way too much information than you wanted about radioisotopes and why we have confidence in our age depth model, I will get into the important findings that our model allowed us to calculate. So here are the downcore profiles of mass sediment accumulation rate for Bishop Harbor on the left and Piney Point Creek on the right in grams per meter squared per year. And while looking at these cores side by side in this manner for the next few slides, it's important to note that these profiles represent different lengths of depositional history, which is driven by higher sedimentation rates at Bishop Harbor and being able to collect a slightly deeper core at the Piney Point Creek location. So Bishop Harbor represents approximately 31 years of depositional history going back to the early 90s. And Piney Point Creek represents approximately 96 years of depositional history going back to around 1925. So Bishop Harbor had a sedimentation rate that was 2 orders of magnitude greater than the Piney Point Creek core, which averaged 20,000 grams per meter squared per year, compared to Piney Point with an average sedimentation rate of 6,700 grams per meter squared per year. Piney Point Creek did experience a twofold increase in sediment accumulation rates over the most recent decade, which includes that 2011 and 2021 discharge event from the facility, suggesting that these events contributed to changes in these rates. I've highlighted the documented discharge periods from the Piney Point facility with those teal shades, which support these discharge events contributing to elevated accumulation rates during these periods, therefore altering the sediment record. And the time frame highlighted in peach, which also show elevated sedimentation rates, could be a result of a few things, such as high magnitude storm events, such as Hurricane Irma that made landfall in Southwest Florida in 2017, or maybe from undocumented anthropogenic discharge events in the area. However, these events were outside the scope of the project and ultimately need further investigation to determine the source or sources of these high sedimentation time periods. Now, here are our phosphorus accumulation rates, which show slightly different trends down core between the two sites, as we saw for the sediment accumulation rates. Presumably because Piney Point Creek was the location of part of the 2021 discharge event, while Bishop Harbor was located the location of more historic events, translating to greater phosphorus at depth at that site. Bishop Harbor had total phosphorus accumulation rates that were orders of magnitude greater than those measured at Piney Point Creek, with an average rate of 230 grams per meter squared per year, where Piney Point Creek had an average of 1.5 grams per meter squared per year. However, the most recent decade averaged 3.4. So this suggests that the site has been more impacted by eutrophication events and more efficient more efficient phosphorus retention or absorption, or a combination of the two. And when comparing the study area to other systems, these phosphorus accumulation rates are orders of magnitude greater than those found in lakes that have been identified as areas of concern due to legacy nutrient pollution, such as Green Bay and Lake Michigan, which has phosphorus accumulation rates of less than 1 gram per meter squared per year. And these are comparable to or greater than phosphorus accumulation rates measured in hypereutrophic lakes in Florida, which help explain where some portion of the discharged nutrients went and highlight how wastewater releases influence nutrient accumulation in estuarine sediments. And from nuclear magnetic resonance spectroscopy analyses, which we conducted to look at what functional groups of phosphorus were present in the sediments, we see that most of this legacy phosphorus is orthophosphate, which is a bioavailable form of P, meaning if regenerated or resuspended to the water column, it could affect primary productivity and potentially ecosystem services in the bay. However, additional analyses like XAS is needed to determine the true mineralogy of it. And relative to nitrogen accumulation rates, Piney Point Creek had greater nitrogen in the surface intervals, likely due to this being a direct discharge location of part of the 2021 discharge event. However, both cores showed an increase in nitrogen accumulation in more recent years, presumably due to the increase in anthropogenic activity surrounding the bay, including the Piney Point releases. And from the bulk pool analysis, we were able to determine that nitrogen being stored at these sites is predominantly ammonium and organic nitrogen, excuse me, both which are readily assimilated into the biomass of primary producers. So with Tampa Bay being a nitrogen limited system, if these nutrients become regenerated or resuspended, it could fuel primary productivity and potentially have events if other conditions are conducive, which could reinforce positive feedback cycles and also highlight the potential for cultural eutrophication to have long-term effects on greater ecosystem health. So from this portion of the study, we found that legacy nutrients are being stored in the sediments in bioavailable forms of both nitrogen and phosphorus. And due to Tampa Bay being a shallow, well-mixed estuary, there is a potential when environmental and redox conditions allow for these nutrients to be resuspended or regenerated into the water column, thereby potentially having these long-term, what we identify as legacy implications on water quality and ecosystem health as a whole. And if you take anything away from this part of the talk, let it be that it's very important that we start incorporating sedimentary legacy nutrients into regional pollution goals, which is currently being disregarded when the EPA establishes nutrient budgets and total maximum daily loads for water bodies, including our coastal waters, which are, again, as I've kind of harped on, are the ultimate receiver of watershed activities. All right, so now I'm going to shift into some of the ecosystem responses that we captured during the study period, particularly for seagrass habitat. So one of the known impacts of eutrophication is seagrass degradation, and since seagrasses are known as indicator species that can provide early warning signs of ecological impairment, monitoring their abundance and other response variables, including tissue nutrients, can really help identify drivers of seagrass change. Nutrient loads can lead to increased epiphytes, macroalgae, and phytoplankton growth, those quick responding primary producers, which cause light limitations and suboptimal biogeochemical conditions that can eventually lead to declines in seagrass health. And when eutrophication becomes chronic, we often see a shift from dense continuous beds to more patchy seagrass beds, which ultimately provide fewer ecological services to the estuary. And so this leads me to the research questions for this portion of the study, where we sampled from 21 to 2023, 2023, at the beginning and end of seagrass growing season, to assess the change in seagrass and macroalgae abundance. And then we followed this with physiological proxies, isotopic tracers, and water quality data to assess drivers that could be influencing these change, while keeping in mind that Tampa Bay is a very dynamic estuary that deals with a multitude of stressors. And you might notice that old Tampa Bay in this figure to the north had really high seagrass loss during the time frame of interest. However, for this study, we did focus on the lower regions due to the wastewater release that occurred there. So at each of our sites, we established 50-meter permanent transects where we collected percent cover, density, leaf area, biomass, and epibiota data. Adjacent to the site, seagrass and macroalgae tissues were collected for nutrients and isotopic analyses. And then the water quality component included sampling both the water column and suspended particulate material for nutrients, while a YSI XO2 was deployed adjacent to each transect that collected a suite of abiotic parameters every 10 minutes for the majority of the study, except for the short periods when the instrument had to be brought back to the lab for maintenance and calibration. So here you can see the mean seagrass percent cover for each station for the sampling period, again, April 2021 to April 2023. And I've denoted with the dashed line here where these stations' seagrass cover lies relative to the Southwest Florida Water Management District's patchy versus continuous seagrass bed designation, which is at 25%. Relative to seagrass coverage at the Outer Bay control sites, these stations had seasonal trends but stable coverage, with cover being slightly greater at the end of the study period. In contrast, the Inner Bay sites showed a general decline in coverage to around 10% or less over the study period, falling within that patchy bed designation of less than 25% cover for the later portion of the study. And this suggests that the patchy bed designation holds significance and could be interpreted as a warning sign that conditions are suboptimal for seagrass. It's been found that patchy beds are equipped with fewer positive feedback mechanisms, such as internal nutrient cycling, sediment stabilization, and even hydrodynamic feedbacks that ultimately can make them more vulnerable to compounded stressors. Seagrass density was evaluated as another abundance metric, which is plotted here as shoot density per meter squared for the three seagrass species observed at our sites, where the horizontal dashed line at 160 shoots per meter squared represents the shoot density threshold that shifts a seagrass bed from trapping and accumulating sediment to an erosional bed. So Thalassia testudinum, turtle grass, which is represented by the solid lines, which was the predominant species during the study, displayed similar trends to mean percent cover, where there is a clear separation in shoot density between the control and inner bay sites, with density generally decreasing at the inner bay sites over the study period. Syringodium filiforme, manatee grass, is represented by dash lines. On the other hand, appeared to show some resilience at two of the inner bay sites, with density at some locations similar to those seen at the control sites. And in certain regions, Syringodium had been documented to be more resilient to certain stressors, including shading, sulfide intrusion, and wave energy. So some of these might be driving some species differences at the site. And then a decline in Haliduli reitii density, also known as shoal grass, represented by the dotted lines, occurred over the study period at one of the control sites. However, the species was only found at two places along the transect, and as it declined, Thalassia increased. So there may have been a competitive advantage for Thalassia, coupled with Haliduli being known as an opportunistic, flashy species that often comes and goes with changes in water quality. So these shoot density results further strengthen our interpretation that a bed as beds grow less dense, it's likely they're struggling to stabilize sediment, shifting them below that depositional threshold and acting as an additional stressor. So with finding declines in seagrass cover and density, with the exception of Serengodium, which displayed some resilience to stressors, we set out to investigate potential drivers of these declines, with macroalgae dynamics being the first focus. Since it's very well documented that the majority of seagrass macroalgae interactions are negative, where seagrass is often at a competitive disadvantage. So here you can see the mean macroalgae percent cover per station per sampling event, where there was high macroalgae cover at most sites that lasted for multiple months following the wastewater discharge event in spring of 2021, where we monitored the control sites weekly through September. And macroalgae cover at the inner bay sites was corroborated by the Tampa Bay estuary program, who had seagrass transects adjacent to ours. And there were also moderate macroalgae and dense cyanobacteria blooms later in the study period that likely also contributed to some level of seagrass stress. So it's feasible to start linking macroalgae to seagrass decline through the creation of light limitation via shading, unfavorable biogeochemical conditions like decreased sediment oxygen levels, and even nutrient competition in some instances. But we suspect that this is not the only stressor on these seagrass habitats. The epibiota community, which grows on the surface of seagrass leaves, can alter the physiochemical parameters at the leaf surface, such as limiting the amount of light that reaches the seagrass, changing the carbon chemistry around the leaf surface, which can lead to seagrass having to use more bicarbonate rather than CO2 for photosynthesis, more energy expelling, and even competing for water column nutrients in certain instances. The epibiota biomass consisted of calcareous and non-calcareous algae, oyster spat, cyanobacteria, and then various epizoans. So our epibiota loads were categorized by low, moderate, high, and very high following Nelson 2017, which is what the dashed lines represent across these figures. Generally, all stations showed seasonal trends in epibiota loading, with loads greater in the spring compared to fall. The control sites maintained low epibiota loading throughout the study. However, the inner bay stations had had epibiota loading that reached moderate at Piney Point and Bishop Harbor, and very high at Joe Bay by the end of the study period. So it can be inferred that moderate epibiota loading or higher can impact seagrass growth to various extents and could be a greater impact on patchy beds that are declining as well. And here we have the bulk nutrients of carbon, nitrogen, and phosphorus that we analyzed on the seagrass leaves, with Thalassia representing the solid lines and Serengodium representing those dashed lines. For percent carbon was lowest at the beginning of the study, with most sites suggestive of light limitation falling below that carbon threshold that's established by Duarte, 1990. And the nitrogen and phosphorus leaf content suggests nutrient replete conditions, except for the control site that had phosphorus limitation for most of the study. So from this data, we can infer that these sites, particularly those in middle and lower Tampa Bay, are vulnerable to eutrophic stressors. And then nutrient ratios and carbon and nitrogen stable isotopes of seagrass tissues were used to further assess eutrophic and light conditions. And similar to the abundance data, the nitrogen to phosphorus molar ratio showed a clear division between the control and inner bay sites, with all sites generally falling outside of that optimal range of 24 to 29 that's shaded in green. Values that fall south of this shading suggest nutrient replete, high nutrient tissue conditions. The exceptions rather include the southeast control site in spring 22 and 23, and Serengodium at the middle bay site in spring of 23, which is that species again that started showing resilience to environmental conditions compared to Thalassia across indicators. Then moving to carbon and nitrogen ratios, all stations but Serengodium at the middle bay site fell within reduced light conditions denoted by that top dotted line. Some also fell within the light limitation category, even more extreme, with the lowest in spring 22, where epibiota coverage was moderate to high, macroalgae cover was around 25%, and there were slightly elevated turbidity in the water column, making light limitation very plausible. Serengodium falling more frequently within that optimal carbon and nitrogen range could be due to a variety of factors, including their root zone depth, nitrogen species affinity, and even growth rates, again suggesting it's more resilient than Thalassia under the environmental conditions that we found at these sites. And now shifting to the isotopic findings, where delta 15N values simply express how much the ratio of 15N to 14N in a sample is enriched or depleted relative to atmospheric nitrogen, which is an isotopic has an isotopic signature of 0 and is denoted by that black dotted line across the figure. So seagrass is known for taking up dissolved inorganic nitrogen, predominantly from the sediment, um, uh, through its root system. However, when nutrients are abundant in the water column, they can also assimilate through their leaf surface. And most often, seagrass have delta 15N values that are greater than 0, which is what we captured at the control sites. Whereas in the inner base sites that have delta 15N values below 0, or in the case of Bishop Harbor, trending more negative over the study period. The inner base sites that have more negative values are suspected to be due to abundant nitrogen at the sites, as reflected in the tissue nitrogen, where the seagrass selectively discriminate against taking up the heavier isotopes, which therefore leads to more negative delta 15N values. And since these values are more negative at the less healthy sites, particularly Joe Bay, in pink. We suspect that as the seagrass dies, the leaf nutrients make their way to the sediments where they decompose and further contribute to eutrophic conditions. And then carbon stable isotopes of seagrass shoots have been suggested as a useful response variable for determining light limitation in a system, because when light becomes limited, carbon becomes less limiting to photosynthesis. So light isotopes are preferentially assimilated, which reduces that delta 13C value. But it's also important to keep in mind that these values can be affected by a ton of abiotic parameters, epibiota loading, and even seasonal carbon sources, so they should be interpreted with caution. But generally, all of our sites suggest levels of light limitation, with the greatest being at Piney Point and Joe Bay. And interestingly, Serengodium again suggests more resilient to low light eutrophic conditions with the least negative delta 13C values. And since I do need to start wrapping up, I'll just briefly mention a couple key points about our water column data that we collected with that YSI XO2 at our sites that were mounted to the seafloor. So temperature was above 30 C for between 120 to 140 days out of our study, depending on the station, indicative of water temperatures that are outside of the optimal range for seagrass, which is about 25% of the study. And there are a few occasions where salinity dropped below 25 PSUs, which is a stressor that others, including the Tampa Bay Estuary Program, have found could be affecting seagrass health, in addition to warm water in portions of the bay, where Bishop Harbor dealt with the stressor for about 10% of the study. And then turbidity was above 10 FNUs for between 8 and 44 days out of the study, and was most prevalent at that Middle Bay site, which is a threshold that's indicative of reduced light conditions. So takeaways for this portion of the study: the data show a decline in seagrass cover at the inner bay stations that is likely attributed to eutrophic conditions, coupled with light limitations created by epibiota loading, macroalgae, and phytoplankton in the water column, as well as stress from high water temperatures during certain periods of the time, during the year. Sorry. And the sites near the discharge locations likely became more vulnerable to compounded stressors as they reached this patchy coverage of less than 25% due to things like loss of positive feedback mechanisms, sediment stabilization, internal nutrient cycling, etc. So this suggests that the patchy bed designation can act as an early warning sign for declining seagrass health and can guide resource managers on where to prioritize seagrass restoration efforts. And then lastly, just some broader conclusions from the entirety of the study. Just as it was documented that the Piney Point wastewater discharge event had short-term implications for the health of Tampa Bay, that was published by a few different folks, including the Tampa Bay Estuary Program. We also found that there are some long-term implications for seagrass health and sedimentation dynamics. But it's important to keep in mind that this event is seen as a compounding stressor, not the sole stressor on water quality and seagrass stress during the study period. And there are some bright spots in this work. There are signs of resiliency, such as with Syringodium filiforme, starting to trend upward at our stations towards the end of the study. Yay! And although we found legacy nutrients stored in the sediment near the discharge locations, there is a study that assessed phosphorus mineralogy in the region following that event that suggests that a portion of the phosphorus is being stored as apatite. So there is hopes that this phosphorus remains bound to the sediment at least to some extent. However, there's still risk of legacy nutrients, particularly nitrogen, and especially with Tampa Bay being a nitrogen limited system, for it being regenerated and resuspended into the water column. So it is important to incorporate sedimentary legacy nutrients into regional pollution goals and nutrient budgets, so that we can get the bay trending positively again. And thank you so much for listening and to a huge team effort that went into this project. And I'm happy to take any questions.
Awesome job, Amanda. That was so cool to see all the work that you've been talking about. I'm really excited. Um,
Thank you so much.
so if you guys haven't seen it already, there should have been a poll that popped up in the chat. And so if you could fill that out when you get a chance, and then please feel free to write questions or raise your hand if you would like to ask questions directly. We'll go into our Q&A session. And while people are filling out the poll, I will start off with a question for you, Amanda. This is kind of a social question, but do you know if there were any repercussions to the Piney Point like company for their discharge and effects to the ecosystem?
Yeah, so there's been one big lawsuit that I think just got ruled in 25 or maybe late 24. HRK Holdings, which was responsible for the facility up until 2010, where they filed bankruptcy, which is unfortunately something that occurs a lot with these larger phosphogypsum stacks, because there's just so much waste. It seems to be that it kind of accumulates and then the infrastructure starts failing and they start walking away from it. So it's in DEP's control. But yeah, there was financial repercussions. I can't remember the exact number. I can pull up really quick. I figured I would have a current status question of Piney Point. So this QR code will take you to the permit that they have now, and I believe that shows who, how things are being handled now, and that might give you some more information. But yeah, HRK Holdings was sued by the state, including FDEP, and that money will be used to close the facility, which they're working on currently.
Awesome, thank you.
Yeah.
I saw Emily's hand first, and then I'll read you some stuff in the chat. Emily, go ahead.
Hey, Amanda, great talk. Also great to see you again.
Yay, hello.
Um, kind of combining your first section and your second section. I don't know if you guys worked on any sediment cores in the seagrasses, but do you think that the seagrasses are storing legacy nutrients? And do you think that as their coverage starts to decrease and they turn into more erosional systems, are we releasing a lot more nutrients and are we like really ignoring some of the really deleterious effects of these declines?
Yeah, that's a great question. And so we didn't collect sediment cores in the seagrass beds. It's probably one of my biggest regrets, coupled with not capturing pore water nutrients. I would say because these seagrass beds are, and this is just speculation,
Yeah,
because this is being recorded. My speculation would be that the seagrass beds are definitely holding some level of material, including legacy nutrients. To what extent, I'm not exactly sure. I would love to further explore that because I think that that was kind of one of those things that got to start drawing the line of how
I'll
many
graduate
things you can take
eventually.
on. Yes, exactly. Um, but yeah, I think that that's a really plausible thought process. And yes, I think that one if we continue to lose seagrass in these areas, we could have even more export of material or resuspension of this material that has legacy nitrogen and phosphorus that is in bioavailable form.
Cool, thank you.
Yeah.
All right, we have two things in the chat. One from Jen Lomberg, who just sent us a link to some Tampa Bay news about Piney Point. So thank you for that, Jen. And then I have another question from John O'Connor. And he says, great talk, Amanda. For the first half of the talk, have you looked at changes in the organic matter loading to the surface sediments following the discharge event? Either just as percent LOI or any carbon 13 NMR work to characterize changes in the organic carbon load.
Short answer is no. Um, was the beginning of the question for that was loading to the water column or just within the sediments? I'm
Loading
sorry.
to the surface sediments following the
Surface
discharge event.
sediments. Gotcha. Yeah, no, carbon NMR would be great. We only had access and only had limited resources to do PNMR, so we had to kind of prioritize there. I think that benthic flux experiments has really been always my next step for these areas to really see what's happening at that sediment water interface and if we are having um kind of like the regeneration of material happening. But yeah, I'm happy to share with you I've got organic carbon burial rates because I calculated all the organic carbon burial rates. So I'm happy to share those with you as well. I don't think that I have them tagged onto this slide. Let me check really quick. No, I don't have my organic carbon burial rates. That was a slide I had to remove because I was over time. But yeah, thanks, John. I'm happy if you want to shoot me an email or I can send you a follow-up with those rates. And also I can pop back really quick to, sorry, this poll thing.
Oh, just like move it. Yeah, can you?
Yeah, this QR code here, John, has my full publication there, and the organic carbon burial rates are in there. So we didn't do LOI, so we don't have organic matter, but we did elemental analysis where we have measured carbon.
Cool. He said, that was a lot. I was just curious. Thank you. Very cool talk. I had another question if I don't see anybody else asking, but feel free to keep commenting in the chat. I was wondering why, and maybe I missed this, but why you thought there was such differences in the age depth cores, like between your the
Mhm.
BH and PP sites? Like
Mhm.
why?
Mhm. Yeah, I think going back to this one is probably the most helpful. So we cored to refusal. So we put these sediment water fissure cores into the sediments as far as we could till we hit something, whether bedrock or otherwise. So we couldn't go any deeper. And so because Bishop Harbor had such, and you can kind of see it, I don't know if you can see my pointer, but
I can.
oh cool. So because Bishop Harbor had such high sediment accumulation rates, the core that we captured, which was 45 centimeters compared to Piney Point Creek being 51 centimeters, the material just over time accumulated like in more recent years so quickly that that
Mhm.
core represented a shorter time interval.
I
So to
see.
get a full record like we did at for the Piney Point Creek core, we would need to go back and either try to core again and get a much deeper core. I would suspect like we probably need another 30 centimeters or so unless sedimentation rates change. But yeah, that's ultimately driven by your sedimentation rate. So if you have really high sedimentation rates, your core is going to ultimately just represent a shorter period of time.
Got it. Awesome. Cool. Any other questions from anybody else? I do have a couple more, uh, but I don't want to take over. All right. Um, I think in one of your last slides, there was like temperature, salinity.
Mhm,
I saw DO as well, and I was wondering if there were
mhm,
any anoxic or hypoxic conditions in your event
mhm.
study.
So for this, Um, so we had DO never dropped below 2, which I think
Mhm.
is generally for 2 milligrams per liter, which is generally usually identified as hypoxic.
Mhm.
We did at Joe Bay, which was where we had the greatest seagrass decline. You can kind of see down here. I should have added another line, but um we did have instances where there was like oxygen stress kind of dropping below 4 milligrams per liter. And again, I know everyone's kind of a little bit different, but
Yeah.
so there was 24 days over our study period where DO dropped to an oxygen stress level. And then the other ones were only like 2 to 8 days. So generally DO was relatively good. It looks like it kind of averaged for most of them between, like 6, sometimes 8, depending on the season.
Yeah,
Um,
that's great.
but yeah, I was actually really surprised. I assumed that the
Yeah.
DO would have been much lower.
Yeah.
So that was, I guess, also a bright spot.
Awesome. All right. Any last questions for Amanda? All right. Well, thank you so much, Amanda. This has been awesome, and we really appreciate you coming. Thank you, everybody who has joined us for this past season of Nature Coast Currents. We'll be taking a break for the summer to get into field work and be coming back to you all in the fall. So until then, take care, everybody.